Hi everyone. Before we get to Haskell and Wordle and all the fun that we're going to have there, I do hope that you'll join me in supporting the brave men and women fighting for their lives in Ukraine and the fine men and women protesting for their freedom in Russia. Let's end this ridiculous war and get back to more fun with Haskell. So we left off last time in our series on writing an analyzer for Wordle in Haskell. We left off last time with a bunch of tests, right? So I can go here, and if I run cabal test, then hopefully, after a little bit of whirring, we should... Oh, I'm surprised it's rebuilding. Okay, so we get fail. The Wordle property failed. In this case, it failed with print and trout. And once again, we see that the problem is, so the Wordle property, let's remind ourselves, is this property, I didn't write it out. Now's a good time to write it out. The Wordle property, if the, for a given guess and answer, the answer must remain a valid possibility after filtering based on the response. So if we guess, in this case, print, then we're going to get a certain pattern of gray and yellow and green. Then we can use that response to filter out what are the possible words that are still in play. And it had better be that if the answer was trout that we used to produce our response, that trout had better be one of the words that's left in the filter. Well, it turns out that this is not the case with our current implementation. And that's because trout has two T's in it. So when here, what would have happened in the response is that the response would have had a green here in the last slot. And this green would have said that you can't have a T here or here or here or here. So trout wouldn't work because trout has a T in a location that we originally thought it couldn't have. And so we have to fix this. And that's going to be the starting point for today's video. We're going to go on from here, and this is mostly going to be about sort of moving around our abstractions and coming up with a better understanding of exactly how to represent this problem so that we can solve it more effectively. That's really going to be the whole sort of theme of the video. So the problem starts with this letter information. So the way that we track sort of where we are, what information we already know in our particular play of Wordle is, let's see. Well, we store our state as a map from characters to letter information. So each possible character of the 26 characters goes to a letter information. And letter information, either we know that it's not in the word or that it's not in this certain set of locations. But as we see with the print and trout example, that's not quite good enough, because if I get a green, I was modeling that as it can't be in any of the other locations than where it was, but that's not quite true. So I want to refine our notion of what we know about a game into saying that, so we have letter not in word, or we can have letter in word, and here I'm going to use a record that for places that that letter must appear, and we're going to have a set of places where the letter cannot appear. So these are going to be the spots that showed up in yellow. Whoops, wrong way. I want to go this way. Okay, so now that we've done that, what we can actually do is we can use Haskell to tell us where we need to modify things. So I'm going to actually try to load up in the REPL here, because that'll make it for easy recompilation. Let's see. Oh, parse error on line... Oh, I don't have a close brace. Let's give that another try. Okay, so now we're getting good responses here. So we have a bunch of places where we've used letter not in location. So let's just search for that, and we can try to fix each one. Not in locations. Okay, there's a bunch. So here, combine. So the idea here is that if I know some facts and then I know some other facts, I want to be able to combine them. Well, if a letter is not in word, then it's not in the word. Here, if there's a mix, letter, I think the new one is called letter in word. Well, still, now we have, I labeled this duplicate letter. This is really contradictory information. And I think that there's ways that we could get that through a duplicate letter, but I'm going to really say this is contradictory info. But if we have letter in Word with here and not here, and then we get another letter in Word, and this is actually fairly easy to do. We're just going to combine these sets. If I know from some piece of information that the letter can't be in a certain spot, and from some other piece of information that a letter can't be in a certain spot, then I just have to combine them. Similarly, if I know that a letter must appear in a certain spot, and it must occur somewhere else, which would be a duplicate, then we can just combine those two. So this works out really nicely. And so all I have to now say is we get a combination of letter in Word, and then here is here 1 combined with here 2, and not here is not here 1 combined with not here 2. Okay, let's see, what else? Where else do we need to edit? Okay, so here, what are we doing? So this is advancing the state. So this is saying if we got a yellow indication, then what do I want to do? Well, previously I just said that it couldn't be in this one spot. Well, I want to do the same thing now. We're going to do letter in Word. And here, because we're creating this fresh, here, well, we don't know anything. So we're just going to write empty, which is from, is that monoid? Yes, that's from monoid. That says this is just sort of the empty thing. Empty is a useful, for any monoid, it's the thing that when we combine them, it doesn't make a difference. So in this case, an empty set is the right one. I could look up the specific name, but it's just easier to use empty. And not here, let's see, not here is going to be, here is empty, and not here, is this singleton, just like this. Good. And then if we get green, this is going to be the change from what we had before. So here I had delete index from list all locations. Well, now, instead of trying to say where the letter can't appear, I'm just going to say, letter in Word, here equals s dot singleton index, not here equals empty. And then we don't need to do all of this stuff. Okay, and then let's line things up so we can see a little bit more obviously what's going on here. Good. Let's see, where else do we have letter not in locations? Well, here, what is this doing? So this is required letters. This is trying to get the set of characters that we know we must have somewhere. I don't know if that's going to be necessary anymore. Instead of just fixing this one function, let's really think. So now a valid word in a particular state has to have no letters in bad locations and all required letters. I think we can actually do a little bit better than that. So I'm just going to leave that around and we'll come back to it. I really want to say required letters in good locations and, right, so the required letters are in the good location. So what do I really mean by this? Well, that every letter that's been marked green really is where we said it was going to be. And the ones that are marked yellow are not where we said that they weren't going to be. I think that's really all we need, isn't it? And no, no letters in bad locations and all required letters. What checks for letters that aren't in the word? No letters in bad, I guess a letter that isn't in the word. Okay, so, and no letters, no bad letters. We'll just call it no bad letters. Okay, so this is sort of a reimagining of this whole thing. I'm going to just comment all of this out for now. And that's because we really have a sort of a new understanding of what we're really checking for here. So, required letters in good locations. Well, let's see. How can we do this? Well, what we really need to do is for every letter in Word in the state. So here we have the mapping. So we need to find every element in this mapping that maps to a letter in Word. Okay, so how are we going to do that? So previously, we went through, where is it? Required letters. That does m.foldL with key prime. That's probably what we need as well. So m.foldL with key prime. Let's just get its type. Actually, I think I'm going to do it this way. If I do foldL with key prime, aha, there we go. I'm going to make this smaller. Hopefully my picture isn't getting too much in the way here. Okay, so foldL with key prime, we can see sort of the pattern down here. This is going to take, some function. We'll figure that out in a minute. And it's going to take the sort of the thing that we're trying to produce. Well, in this case, it's going to be a bool. And if there's nothing mapped here, then the required letters in good locations is going to be true. If we have no information at all, then the required letters, there's none of them, so they're all in good locations. So that's fine. So that's our sort of default value. And the map that we're going to be operating on is mapping. Okay, so now we can write where go is going to be a function that takes a bool and let's see here, and then takes a key and a value. So the key is in this case going to be a character. The value is going to be letter information, and it's going to produce a new bool. But actually, now that I've done this, I wonder if there's another function in the map interface that will give us what we want. So here I want to look at map. So I think if I click there, I'll get what I'm looking for. Yes. Because this foldL, it's a little bit confusing with these bools. I bet there's a better way of doing it. What I really want, is something like this. This will give me a list of the possible different key and value associations here. And then I can process this list using other techniques. Let me just see if there's another thing that will work well. Oh, toList. That looked like the same as assocs. Oh, an alias for to ascending list. And it says subject to list fusion. I don't really care whether it's ascending or not. I'm just going to use toList. I like toList. And it says subject to list fusion. So that means in an optimized program, this intermediate list might disappear if we immediately consume it, which is exactly what we'll do. So I think that's pretty good. Let's get rid of this. Instead of map foldL with key prime, instead, what I want to do is I want to say, so we're going to have mappings equals m.toList of mapping. So just to remind us, this is going to have type list of car letter information. It's going to have this list of pairs. And then, let's see, for each pair, I want to check to see that they're all okay. That sounds like a use of the function all. So if I say all check one mappings, then I think that's probably what we want. And now this is quite a bit simpler than this foldL with key prime thing that I was going to do. So check one mapping is going to take this pair, this letter information, and it's going to produce a bool. Okay, so we get the letter, and if we have letter not in Word, well, actually, at this point, if I know that the letter isn't in the word, then I can already check against this particular word. So maybe we don't need this no bad letters thing. Maybe this is going to become much simpler than we had before. So this says if the letters and letter not in Word, then I want to check not letter lm. This is going to be, I guess, v.lm. Is that a thing? Data.vector.lm. Hello? Yes, check if the vector contains an element. That is what I want. I'm a little worried about performance here, but I have some ideas about that, so we'll come back to that. So not letter is an element of the word, of get letters in the word, right? Because we have to extract out that vector. And then check one mapping. We have letter, and then we get letter in word. Here is Let's see, here is going to be yes locations. Not here will be no locations. And now we need to check to make sure that for every yes location, this letter is in that spot in the word. I think we're going to need the word letters a bunch. So we're going to say word letters is, let's see, didn't I have a type for this? If I look over here, vec5. Yes, I thought I had a type for that. So this is a vec5 of car, and word letters is going to be get letters from words. Did I get that right? Is it get letters? Yes, get letters. Excellent. Okay, good. And here I can have word letters. And then now down here, I want to make sure that for each yes location, that indeed that letter is in that location. So now to do this, I'm going to need, this is a set, and I need to do something for every element in the set. So let's look up data.set. Okay, so over here, this is kind of like a query. I mean, I could probably get a list again. Ooh, maybe I can get a list again. That might be easier than other things, because what I really want to do is I want to do another all. Ooh, maybe they're just all. Let's look up all. In fact, I bet that is here. There's probably a better way to do this. If I do colon, man, that didn't show up. Let's see, this is one kind of fold. Actually, I have an even better idea. I know exactly the type of the function that I'm looking for, so let me just look that up. I want a function that gives me, it starts with a set A, and then a function from A to bool, and then gives me a bool. All, and it works over foldable. Of course it does. So I can just use all over foldable, and it will work over a set. Of course it can. Why did I not think of that? Okay, excellent. So let's see, where were we? Were we here? No, that's advanced state. We weren't there. We're down here. No, we're not even here, are we? Here, we're down here. So now I want to see that for all letter is in location, yes locations, and we're going to have to do something with the no locations, but letter is in location. This is going to be from a location to bool, and it's just going to check to see that if we look at the word letters and if we access the location, oops, I forgot to bind it, that in fact equals the letter. I need to pass the letter here. So all letter is in location. What letter? This letter. And we can do that. But actually, I want to do this differently. Instead of having this letter is in location be this separate function, I'm going to do another where binding, and then that way I don't have to pass this around. So let's move this in, and then now I can just access letter because it's in scope. So that's a little bit simpler. And I can delete all of this stuff. So we want to see, is the word letters at that location, is it in fact the letter that we're looking for? That's the exact check that we want. So that's good. And then all something no locations. Well, we want to have all, not letter is in location. Yay! That makes me so happy. Okay, does this work? I bet it does, but I'm not sure. Ooh, there's 3 nested where clauses. Oh, well. Okay, so now if I've done this, I would love to test this, but I think we're still in a slightly bad state down here. So let's reload. But there's only one error, line 135. Hopefully this is easy to fix. It's this required letters. I don't think I'm actually using required letters anymore. No, I'm not. So let's just comment that out. I'm going to delete this quite shortly, but I do want to make sure that the new thing works well before I get rid of what we have. There's still a problem. Line 191. It's in this example down here because I don't have letter not in locations anymore. So instead I want letter in word, and here it's going to be, this is representing a yellow. So here is going to be empty, and not here is going to be this singleton list containing 2. And then down here, this is letter in word. And here, this is a green. So here I want it to be the singleton list containing 4. Remember, 0 indexed. And not here is mempty. And then we need to close all of our things like that. Let's see, does this work? Oh, no. Still something, no bad letters. Well, line 140. Let's see. Oh. The no bad letters just sort of came automatically. Oh, and then there's no reason to have this as a separate thing like this. Let's clean this up a little bit. Move that up. And then now I can get rid of this. And I can get rid of this extra where. And if I do this, I want to, there we go. I can do that. Excellent. Okay, let's try that. Reload. Oh, defined but not used. Oh, that's just a warning, but I don't like things that are defined but not used, so let's get rid of that. Okay, so this is actually, the code simplified quite a bit. That's often a good sign. Now, I want to check. So peach state is this state. So we have filter words. Oops, I scrolled off the type. Filter words, peach state, final words. Oh, not in scope. I have to import Wordle, I think, to do this. And it's thinking, oh, so now there's a whole bunch of things. So this is, we've guessed peach. We've gotten this particular response. Let's see, does that match up? So there should be no P, no E, and no C in any of these words. Does anyone see a P, an E, or a C? I don't see a P, an E, or a C in any of these words, so that's good. Then there should be an A in every word, but it shouldn't be in the middle spot. So already we have a problem because this does not have an A. So we have to go back. There's something not quite right here. So check one mapping. Aha. So letter is in location. Not only do we have to check that the letter is in location in all of the yes locations, we have to check this, but then there's one other check. We have to check that it is in the word somewhere. So we want to check and letter is in the word somewhere. So actually 3 conditions for letter in word. It has to be in all of the good locations, not in any of the bad locations, but it has to be somewhere. Okay, let's reload. Try again. Aha, this is a much smaller list. But larger, you might note, than the list that we saw a few videos ago. So here, again, there should be no P, E, or C anywhere. That looks good. We should have an A in every word, but never in the middle slot. That is true. And we should have an H at the end of every word. Once again, true. Excellent. Now, there could be some other word that should be here that we don't see, but that is what we can test over here with the Wordle property. So let me close out of here, and then now I can do cabal test, and we'll see what we get. Aha! So here, we actually had encoded last time that what the answer to the peach state should be as a specific unit test. Well, let's just change that and say now, I have to get this in order. This really shouldn't be checking for order, but it will because I haven't defined it otherwise, but that's fine. And of course, the word that I'm adding has a repeated letter because that's where we ran into trouble last time. So let's give this another go, and we can see if that Wordle property holds. Test passed. Excellent. So this Wordle property, as I've written it, holds. Every time we make a guess, the answer that we use to formulate the response is in the set of words that is left after filtering. But in some sense, this is the positive Wordle property. I also want to make sure that all of the words that we've eliminated should indeed be eliminated. So for that, what I want to do is I want to have the inverse Wordle property, or I shouldn't say inverse. Maybe I'll say converse. It's probably closer to it. Wordle property, guess, answer. And what is this going to be? So I'm going to get my response, same way I did last time. And we're going to get our new state the same way I did last time. But now I don't care so much about the words that have been retained. I care much more about the words that have been lost. So to do that, instead of filter words, I really want partition words. So let's go to Wordle here. We're going to have to, instead of just having filter words, I really want partition words, which is going to have mostly the same type. But the result here is going to be two different components. Where the first component are going to be the good words, and then the second component is going to be the bad words. So here, partition words, and I hope there's v.partition that just does exactly what I want. And then here, instead of calling v.filter, well, that's not so bad. I'll just call it v.filter. I could just take first of this, but I suppose that's slightly less efficient. Okay, so now if we go over to my test, now I can have filtered out equals, I don't like using second when I don't have to, so let me just do it as a little pattern match here. So filtered out is going to be partition words, new state, final words. And I want to make sure that my answer isn't in these filtered out words. So not answer v.elem filtered out. Actually, now that I'm doing all of this, I think I've done something slightly wrong. So here, I feel like these two things sort of imply each other somewhat. So this is checking to see that the answer is retained. If I did over-aggressive filtering, then this would fail. What if I do, what I really want to check is under-aggressive filtering, which is to say that everything that's retained actually produces the same response. So this converse, this is just all wrong. Scratch that. It's good to be critical of what we sort of, once you get to the end, you should think back. So instead, I want to say that, you know, what is this? This is valid words with same response. So once again, we're going to do these steps, actually all of the steps, and then here I want to check that every word that's left would produce the same response. So if I do respond to guess, this would be, this is a function, so filtered word, respond to guess filtered word, which should be the same response that I got, that I used to sort of build my filter. And we want to check this for everything in filtered. So this, neither of these implies the other. Oh, wait a sec. That's not quite true. So if answer is in filtered, then this is always going to be true of that. But neither of these are related, but they're not the same. I don't think so. Okay. So here, now that I've defined this valid words with same response, I can add this to a new property-based test property. It's the same response property, valid words with same response. Okay, let's give that a go. And we're going to build this. Test failed. Papal and pupil. Okay, fine. So what is this saying? So the Wordle property passed, but the same response failed. Papal and pupil. So let's think. So somehow something in here went wrong. So let's just work this out. Papal. So my response, so the guess is papal. The answer is actually pupil. So my response here is going to be, well, things are very good here, aren't they? So my guess is going to be green. The P's match up. This A, well, now, what are we going to get as a response here? I think what we're going to get is this. Now, what's strange here is that this A actually does appear in the answer. And so I am very curious what happens in practice. So let's jump back into the REPL. And once we're back in the REPL, okay, now what I want to do is let me import Wordle. And I really wonder what happens with papal and pupil here. So what I want to see is I want to not get response, respond to guess. That's what I'm looking for. What is respond to guess papal versus pupil? Oh, couldn't match. Oh, I need to enable overloaded strings. And so if I respond to guess here, I get G, Y, G, G, G. The water is getting deeper and the ice is getting thinner. So the reason I'm disturbed now is because I realize that when we get a gray answer, that doesn't actually mean that the letter isn't in the word. It means instead that sort of the letter is fully accounted for in the word or something. And we see here, because I don't really want to say that A isn't in the word. So now we're realizing that things are even harder. Now is probably a good time to think about changing our representation. So as I've been thinking about this between videos, I realize that this vector of characters representation, I don't think it's really the best. Instead, I want to think of each Wordle word not as just a sequence of characters, but instead a mapping of characters to the locations in which it appears. So I'm going to go over here to words, and instead of making Wordle word a vec5 car, we're going to fundamentally change the representation here. And instead, I want this to be a mapping from characters to, well, not quite locations, because then each character could only have one, but I want this to be a mapping from characters to sets of locations. Now, given that there's only going to be a few different characters and at most maybe 3 locations, is there a 5-letter English word that has 4 of the same letter? Erie is kind of close, but that's actually an I there. But in any case, there's not going to be so many elements of this set. So I think we could probably do better, but I'm focusing more on correctness right now than on efficiency. Okay, so I want this to be a map from characters to sets of locations. I could still write get letters. And in fact, I think that I'm going to need to be able to show one of these things. So let's see here. How can I need to understand this new representation. What I really want to do is vec5. How am I going to convert this into a vec5? I could do so really inefficiently by starting out with like a vector of 5 blanks, and then I update that several times as I access my pairs in the map. But that's a bad way to do it. I don't like that at all. Is there a better way? It's kind of hard to imagine a better way. Really what I want to do is I want to take, my first step is probably I need to invert the mapping. Aha! I want to invert the mapping, and then I can do it. So I don't know what I'm going to write up here, but where inverted mapping, this is now going to be a map from location to character. It's not going to be set of character because I know I have an invariant. Each location appears only once. That's an important invariant. And so we have to be careful that that's indeed true. And we're going to come back to that in a minute. Let's see. So here, get letters is now, because of this invariant, I know that inverted mapping, we can do it. And so here, this is going to, I'm going to use m.toList to convert the mapping into sort of a list of car set of location pairs. And then for each one of those, I'm going to have to turn that into a set, and then we're going to do a sort of a fold. So I think I actually really want fold map. Wonder, do we have that function directly in data.map? I don't really want data.map.internal. Can I just get data.map, please? Contents, data.map. Oh, there's not very much here. Oh, no. I don't want lazy. I don't want no laziness. Data.map.strict. Okay, let's do that. And here, I want fold, but I kind of want just sort of fold mappy kind of thing. Does any of these work with respect to a monoid? Fold map with key. Excellent. That's exactly what I want. Okay. This can be asymptotically faster. Excellent. Asymptotically faster is great. So here, fold map with key. And I don't know exactly what this is going to be yet. Mapping. So go in this case, this is m.foldMap with key. Go is going to take the key and then the value. So in this case, the key is a character. The value is a set of locations. And this, I'm just attempting at this point to create the inverted mapping. So the result is a map from location to car as I'm inverting. So letter and locations. Well, now here, I'm going to want to do another fold map. This is going to be over sets, but set is foldable, so I can just use the foldable fold map. So I can say fold map. Let me just sort of remind everyone about fold map. So fold map allows me to write a function that takes elements of my foldable. I guess this is this top one. Elements of my foldable, convert them into something else, and then as long as those things can be combined using a monoid operation, then fold map will combine all of them. Okay, that's exactly what I want here. So fold map, and then, this is going to be go map. This is going to be something like go set. Maybe we'll come up with better names for these in a minute. Fold map go set over the locations. But here I already know the letter. So this is going to be where go set, let's see, this has to be a function from location to my final result, where for each element in the set, I want to make a mapping in that location. So this is probably going to be something like m.singleton. Do I have m.singleton? Is that a thing? Please, singleton, : yes, ka to map ka. That's exactly what I want. So here we're going to say m.singleton of letter loc. And I think that's good. I think that will work. And then once we have the inverted mapping, then we need to build vector from the inverted mapping. But this should now be easy because I have this nice mapping that should tell me exactly what to do for my vector. So let's see, is there a good function for building vectors? Let's see here. So this is going to be in data.vector. And I bet there is. So construction. So I don't want to do this, replicate, no, generate, construct a vector of the given length by applying the function to each index. Oh, yes, that will work beautifully. Generate, excellent. Okay, let's get rid of this. So build vector. So this, I don't even need to have this as a thing. I just can do it right up here, can't I? That would be much better. So we're going to say v.generate. Oh, I've already forgotten what its type is. It takes an int, the size. So this is Wordle word length. And then it's going to take some function. This is going to be lookup letter, where lookup letter takes the index, and then it has to return the character at that index. So lookup letter is just going to be looking up in this map. So how do I look up in a map? I think it's also bang. Is it also bang? Let's look at the map thing here. Yes, here. Calls error when the element cannot be found. That's appropriate because I'm really hoping that we only have good indices here. Otherwise, we're in deep, deep trouble. Again, I'm hoping a future video might come back and come up with ways to avoid partial operations like this. In fact, because, well, bang is an easy one. I'll come back and I'll find this. Map KA to K to A. So this is map KA. So this is mapping look up, the index. Okay, so that's get letters. And the real reason that we need that is that there's no other good way of making a show instance. So here, instead of using pattern match, I'm going to have show word is really going to be toList of get letters of word. So the fact that I'm using toList here, this should be v.toList. I think we're going to have to add some new imports here. Maybe I could have gone directly to a list. Maybe that would in fact be an improvement over what we have now, although that's not very clear to me yet. Okay, let's reload. There's going to be all these problems. Okay, nothing named v is imported. We should fix that. So data import qualify data.vector as v. And then, actually, are we even using text anymore? I don't think we are. So kill that. And then we still need data.string for isString. Let's reload. Not in scope vector. So let's find uses of vector. And we can make this v.vector. Good. And reload. And now, oh, there's no m. That's no surprise. Import qualify data.map.strict as m. Oh, now there's no location. I must have defined that over here. Yes, and that is good that it's moving because it really should be quite close to this definition because they both have to do with the number 5. Oh, and now there's no sets yet. So import qualify data.set as s. Aha, okay. So now this loaded variable not in scope, go map. Oh, that's because it's called just plain old go here. Variable not in scope from list. Oh, here we want v dot. Oh, no. So this is the point at which we have to build this funny representation of a Wordle word from a string. So we're going to call this mcWordle word. And sure, it can go from a string in this case, because that's really what we'll start out with, to a Wordle word. So now how are we going to do this? Well, this is just going to process the letters one at a time, and it has to build up this mapping, but it needs to do this with the index. So what I want to have is a normal map won't work. Map accum is kind of the wrong thing. I think what I really need is fold, but instead of writing a fold, string is a list, so I'm just going to write a nice little recursive function. But my recursive function needs to start out with the initial index, so it has to be a locally defined one. So go is going to take int, this is sort of the current index I, I'll call it, remainder of words starting at index I. You know, we want to relate these things. And then this is going to produce a Wordle word. And so go index, and then we're going to have, well, if the input string is empty, then we're done. Oh, we need an accumulator. So we have to have an m.map car to s.set of location. But I've used this now, this kind of mapping, I've used this a couple of times. So maybe what we really should have is we should have a type synonym for that in case I change it. So this is, I'm going to call this a word representation. It's going to be a map from characters to set of locations, but this maintains the invariant. Whoops. What have I done? I want to take this and put it there. Okay, so this is going to be it's going to wrap up a word representation, giving us a chance to maintain that invariant. Maybe it makes more sense to state the invariant on the new type where we can actually uphold it as opposed to on the type synonym, but my guess is all of that's going to come out in the wash in the end anyway. So now that we have this, we can start using it. So, oh, no, I don't want to change that. That one's okay. Maybe it's just here, actually. So this is a word representation. But in the end, we're going to produce a Wordle word by wrapping it in the constructor. So here we have an accumulator. We start out with the empty word representation. And in the end, if there's no more letters to process, then we just use the constructor McWordle word, so it's just McWord, excuse me, on the accumulated representation. Otherwise, we have some letter followed by the rest of the letters. And then what I want to do is I want to take my accumulated representation and add to it. So for that, I have to look in map, and this is insert, isn't it? Insertion, insert KA map, okay? So this is going to be m.insert. The key here is the letter. And, oh, but I can't insert a set because maybe I've already encountered this letter somewhere else. So I have to be a little bit careful. So insert isn't quite the thing I'm looking for. Do I want adjust? Update a value at a specific key with the result of the provided function. When a key is not a member of the map, the original map, no, that's no good because I still want to be able to add. Adjust with key, no, that's still the wrong thing. Update. Updates the value x at k if it is in the map. If fx is nothing, the element is deleted. If it is black, the key k is bound to the new value. No, I think that's not quite right. Alter. Alter might be the thing that I need. Alter is quite general, but I think it's going to be the right thing here. So alter, it alters the value x at k or absence thereof. It can be used to insert, delete, or update. Well, I'm never going to use it for deletion, but insert or update. That's fine. Let's use alter. So here we don't need m.insert. I want m.alter, and then this has to take this alter function. And then it takes the key and the old map. So the key is going to be letter, and the old map is ac, where alterfun. So if this gets nothing, that means that this key, this character, wasn't in the map at all. And so that means I want to make a singleton set that just contains this particular index. If it already is here, so then this is already a set of locations. Let's name that more informatively. Then I'm going to extend it. So now we need to do a set operation, data.set, insert the thing into the set. Okay, so this is s.insert index into the existing locations. Okay, and that should work. So the key question is, does this satisfy the invariant? Each location appears only once. Well, yes, it does, because, I've been very silly. I haven't been recursive. This m.alter, that's really, this called m.alter, that's going to be the new accumulation. So I can just put this in here. New ac is this thing. And actually, what I want to do is I want to call go again with the new ac, so we're building this map up with the next index and the rest of the input string. So the fact that my representation invariant here is going to be satisfied by the fact that I'm always incrementing the index at each step. Okay, let's reload. Oh, now we get other errors. Let's start at the top one. So line 20. What's wrong on line 20? Couldn't match this with actual type that. That's because, no, this looks okay. Couldn't match expected type this with actual type. Well, that is the actual type. Why is it expecting this type? v.generate is applied to 3 arguments. Oh, but its type only has 2. v.generate is applied to 3 arguments, but its type Oh, it's Wordle word length, lookup letter, inverted mapping. Inverted mapping is, now I'm confused. Oh, when we do lookup letter, that is working on inverted mapping. I don't need to pass it up here. Okay, that probably will resolve a number of errors. Couldn't match car with int on line 32. Let's see. Oh, it says we've gotten this backward because I want a map from locations to characters, and indeed I've gotten it backwards. Yay, type checking. Yay, type checking. Variable not in scope from list. Yay, scope checking. This is no longer going to be this thing, but instead this is going to be McWordle word of cars, so I can just drop the cars, and from string is going to be McWordle word. And, oh, yay, it's compiling. Excellent. Okay, so one thing I want to know, if I type McWordle word of hello, we get hello back. Now, that looks really trivial, but it's not at all. This is actually a test to see that McWordle word and get letters are inverses of each other. Although one returns a vector and the other takes and the other is a string, but they should be inverses of each other. Hey, that's a new property. Let's add it to our property checking. So here we can add another property-based test. Test property Wordle word construction. And so this is going to be, this is the property that for any string of length 5, so now I need to know that I get strings of length 5. So really now this suggests that my vec5, maybe that really should be a new type so that we can create arbitrary things of that length. So let's put this on hold for now. And we can go back here to words. So this, where's vec5? Vec5, oh, this really, again, should be with sort of all of the 5-y things. A Wordle word has 5 characters. This is where all of these definitions are. So here I've said that this is a type. One thing that we're discovering while working here is that many times we start out with the types in them and we realize that using a new type is actually better. So in this case, it's still going to be mcvec5 a vector, but it's always going to have 5 elements. Now, because it's a new type, then over here in test, what I can say is I can say arbitrary, instance arbitrary, although this is going to end up to be an orphan instance, but I actually do want to keep these instances over here away from words.hs because I don't want my primary library to have to depend on QuickCheck. Really, that's a testing thing. So I'm going to put my instance here. So arbitrary A, for any arbitrary A, I can make an arbitrary, if I spell arbitrary, vec5 of A, where, well, let's see. What I need to do now is I need to generate a vector of length 5 let's see here. So I want to generate a vector of length 5 that has the right, that where each element is arbitrary. I think that I can do that, but now I'm a little worried because I need something that checks this invariant. So we're going to have mcvec5. We're going to have get vector, which goes from a vec5a to a real normal vector of a. This is going to be simple. Mcvec5v equals v. There's nothing to check there. But when I make a vec5, this goes the other way. I'm going to check the invariant. So that I want the length of my input to equal not anything but Wordle word length. And then I can call mcvec5 of v. Otherwise, we've done something very naughty, and I'm going to error. Again, I do hope to come back and then use my type system to help avoid this. Okay, so now I have mcvec5. Good. But now I still need to create a vector of length 5. Let's see, what do we have in data.vector that might help me do this, where the thing that I'm going to call is actually monadic. Aha! Replicate M. Execute the monadic action the given number of times and store the results in a vector. That's exactly what I want. Excellent. So I just call replicate M, and this problem is solved. So I can just say muck vec5. Well, I have to now use do. So vec is going to be replicate M, right? And I have to give it the length. So this is going to be v.replicate M of Wordle word length. And then I say MA. Well, what's the thing I want to do is arbitrary. And then I can return muck vec5 of vec. I like that. That's good. In fact, and this denotation is sort of obscuring really what I want, so I can just do it this way, and that's a little bit cleaner. Okay, good. And let's see here. Now, can I reload? Oh, error, blah, blah, blah. Expecting one more type. Oh, words, line 18. Line 18. Oh, haha, of course. This builds on A. Okay, good. Load. Oh, now there's all sorts of other problems. Okay, couldn't match these two types, because previously they were just type synonyms, but now they're not. So line 35 has some trouble. And that's because I'm just calling v.generate, but actually mcvec5 is appropriate here because this is always going to produce something of the correct length. Good. And then we reload, and line 68. So this is show. So here's v.toList of get letters. So get letters is going to return to me. What does it return? It returns a vec5. But I can't just call v.toList because that's a vector thing. So I really need to say get vector here to extract out the actual vector so that I can then call toList. And hooray. Oh, nope, no good. No instance for eq. Well, that makes sense. So my new type, let's deriving eq, and let's just do ord2 in case we need it later. Still more type errors. Let's see, line 18. Oh, now these are in Wordle, so I guess we're making progress. Now here, it's once again, we're having trouble getting back and forth between these. So I've called get letters, and get letters, this is really meant to be a vector. So actually, maybe a better thing to do would be to go over here and say get letters doesn't return a vec5, but returns a v.vector. Oh, wait a sec. So this is a little bit confusing. So Wordle word, I do kind of want this to produce a vec5 because it should always be a vec5, although that's not quite captured in my invariant. Each location appears only once, and the other invariant, it's not each location appears only once, it's locations 0 through 4 each appear only once, and exactly those locations. That's the very specific invariant, and it means that this will indeed be a vec5. So I do want to keep that as a vec5, actually, as the result of get letters. But then in this case, I'm doing some processing over them, so then I need to get vector of get letters. And we're compiling. Okay, and line 41. Let's see here. So once again, we're going to have this v.toList problem. So here I need to get vector. Line 45 has this problem. v.fromList. Oh, this is muck response. Well, now here we really need to call muck vec5, right? Because a response is a vec5. Am I sure that this will always be exactly 5 letters? Oh, I did actually check that up front. But now it means I don't need to check redundantly here. So this, we can actually simplify this somewhat. And we know from, No, I take that back. I do want to keep that. So this v dot from list, because it's mapping over something that has the right length, this will also have the right thing. So mukvec5 is appropriate here. Okay, let's see if there's other errors. Line 56. Let's see. So this is get letters, and now we're using v.zipWidth. But v.zipWidth really should be producing a vec5 itself. So I think what I want to do is I want to take this vec5 thing and actually have zipWidth defined over vec5s. So I'm going to call this zipWidth or vec5 zipWidth. And so here I want to say that we have a vec5, well, it's zipWidth, isn't it? So it's A to B to C to vec5A to vec5B to vec5 of C. And now here I could sort of write all of this out. Instead, I'm going to use a nice feature of Haskell called coerce. And coerce allows me to take an existing function, and if the only difference between the existing function and the new one is just that it's wrapping or unwrapping new types, I can use coerce. And so if I do use coerce here, then I know that these are two vec5, so I don't need to recheck because I know that zipWidth doesn't change the length of things if the lengths of the two inputs are the same. So let's give this a try. I think we're actually going to run into trouble here. We don't have coerce in scope, so let's add it. Import data.coerce. Still expecting some problems. Yes. So this is a nice little sort of coerce gotcha, which is, I said that this will convert between two types as long as the only difference between them is sort of new type wrapping and unwrapping. Well, in this case, my zipWidth, we don't know sort of what I'm wrapping from and what I'm wrapping to. So I need to be a little bit more specific here. So my v.zipWidth, this is going to be wrapping from A, B, C to the new one. And that's because my coerce might change A to something that wraps A or might change B to something that wraps B. This is a use of type application, so we're going to need a new extension up here. And let's give this a try. Not in scope. No, I suppose they're not. So let's use scoped type variables to bring these into scope. Ooh, that worked. Okay, excellent. So now we're back over here with some trouble on line 56. Oh, and that's because I'm still using v.zipWidth. I really want to say, whoops, vec5 zipWidth. And let's see how that fares. Oh, running into more trouble. Let's see here. So line 61. So here, once again, we have this, but actually this is another time I can use vec5 zipWidth. Did I capitalize it? I think I did. Whoops, too far. Yeah, I did. So this should be a capital Z. Okay, line 115. Oh, now we have zip. Well, isn't that convenient? I can define this in terms of, I can say vec5 zip with, and the thing that I'm zipping is the tuple constructor. I could define that separately, and maybe I will in a minute, but for now that should get me past this problem. Oh, now we have v.ifold_l prime. Let's see. This looks pretty cool, but here I really don't want to try to re-implement this for vec5, at least not yet. So here I am going to use get vector so that can operate on the vector. And then now up to line 148. And then now we have this v.elem. Again, I can just use get vector here. And I think I'm going to need it again down here. So in fact, because I need it in, I think, all of these places, I really don't care that this is a vec5 in this case. I don't think. Let's see. Where do I use word letters? Do I ever take advantage? This access really does take advantage of that. So I don't want to change word letters into something else. I want to know that it has 5 elements. Okay, line 153. Well, here I actually don't want to convert this to a vector. Instead, I'm going to say vec5 lookup and then I'm going to make vec5 zipwidth, vec5 lookup, and this is going to be a vec5a to int to a, where we have a very important precondition in the range 0 through 4. But vec5 lookup can just be implemented in terms of the existing bang operator. Okay, let's see what we think of this. Couldn't match types. Oh, this is over in words, line 36. Oh, yes, I need to coerce that. And I'm sure we're going to have the same problem we did a moment ago. And then so we need to bring this into scope here. Okay, good. That worked. Everything worked. And you know what? While we're doing this, let's define vec5 zip as well. And this is going to be v.zip. Let's give it the right type. Doesn't have that. It just has A and B. And this is AB. And is it happy with that? Yes, but now I want to use it in the spot that I used this funny operator here. Okay, how are we faring? Good. Whew. But actually, remember, I was over here and I wanted to write a test. Right? I had written this arbitrary instance, and let's see. So test property, Wordle word constructor, and I want to say, what do I want to say here? I want to say that an arbitrary, well, for any word, what was it that I wanted to say? So for any vec5 of cars, so this isn't really a cars, this is just going to be a vec5 of cars, then constructing the word and deconstructing the word are inverses. So what are these functions? These functions are McWordle word, which converts from a string to a Wordle word. Oh, I don't want to convert from a string anymore. This really should be a vec5 of car. And now, is this the right thing? Now we need to update this. This go is really very much like an I fold L prime thing. So we're going to, this is v.I fold L prime go. That actually might just kind of work. No, maybe not exactly. I think I have my types slightly wrong. I fold L prime. Yes, this is the one over vectors. It's the thing we're producing. Good. Then the int, then the contents. Oh, it's not going to be the remainder of the word anymore. Instead, it's going to be current character. And so this sort of base case is no longer here, but we have this. And now all we have to do is not do this, but produce the new word representation, which is, of course, this call here. Okay, how do we feel about this? And then this is probably at the very end going to need a call to McWord, and that might just kind of work. Except that the vec5 coming in, I need to, let's see, v.I fold L prime. Oh, we don't need the 0 anymore, but we are going to need get vector of vec. Again, there's something slightly funny here because my word depends on the length being correct, or not the length being correct. My word depends on this particular invariant, and I'm sort of losing that because I'm going through vector, which might not maintain the invariant. So if I come back and try to make nicely typed things, this is going to be some trouble, but we'll cross that bridge when we come to it. Let's see. Sure, we're going to get new type errors here. So line 77. Now from string is no good because it's not a vec5. So really what I want this to be is mcvec5, and then this mcvec5 takes a vector, so this has to be v.fromList. Let's give that a try. I would like that. Okay, back to the testing. Okay, so if I have cars, which is now going to be a vec5, then I want McWordle word and get letters to be inverses. So, oops, I want to go to test. And so for every cars, get letters of McWordle word of cars, whoops, spell, must equal cars. That's the property. I don't even need to define it separately. And we should probably have it be inverse the other way too. So Wordle word deconstruction, I suppose. This isn't very good names. But here for a word, I want McWordle word of get letters of word to always equal the initial word that I started out with. So let's give this a try. So I'm going to do actually cabal REPL test, I think, because I want to load this test file so I can interact with it, because it's probably not going to work the first time. Okay, so let's see. So there's some compile error. That doesn't really surprise me. No instance for show of vec5. Oh, well, that makes solid sense. So let's go back here. And where is vec5? Do I want the built-in show instance? Oh, arising from a use of test property. Well, okay, sure. Let's just use the built-in show. Oh, but I don't want to see vec5. What I really want to do is say I want the show to be exactly like vectors. So that means I want new type show. If I just use sort of the default show, then we'll see mcvec5 in the output. I don't want that. So I want to use new type deriving. So let's go down here and try to reload. Oh, we need deriving strategies. And reload. And now we need generalized new type deriving. Okay, and reload. Ah, excellent. Okay, so everything loaded. And now here, I want to, before just running the test suite, I actually want to say, can I say quick check? No, if I say import test.quickcheck, can I say quick check? Yes, I can. So I want to see, does this property, I really wish I had a name for it. So let's give it a name. We're going to call this Wordle word construction. Equals that. And then I'm going to say Wordle word destruction equals the other one. I still don't really know if I'm getting these names at all sensible. Names are hard. Wordle word construction. Wordle word destruction. Okay, let's load. Good. And let's. What do I want? What did I want to do? Oh, that's right. I wanted to just run quick check on Wordle word construction. Wow, it actually worked. I didn't think I really expected it to. Quick check on Wordle word destruction. That also works. Yay! So what have I just ascertained? I've just ascertained that these functions, which are quite non-trivial, actually are inverses of each other. So that's really nice. In fact, I sort of didn't really expect it to work. So let me intentionally add a bug just to see what happens. What's a good bug? So a good bug to do is maybe if this alter fun ignores its input and always just returns singleton index. I almost made that mistake, in fact, right? This would mean that if we have repeated entries, it's not going to work. So I've now made that change. Let me reload. And then now, oh, look at that. Oh, map key is not an element in the map. Well, that's one way for things to fail. And then if I run this, oh, we also, yes, we get keys are not element to map. Okay, good. I guess it's working. Excellent. Okay, this was a long journey. I still don't think we've fixed the papal versus pupil problem. I think we're going to have to return to that next time because this video is already very long. I'm sorry for that. But lots of fun things to do. So I want to sum up a little bit some of the things that we've discovered today. So one is that we are slowly making our representations more abstract, right? Instead of just storing a vector of characters, now we've glorified this to this other more intricate representation where we have a map from characters to sets of location, because it'll be easy, for example, to remove elements from this set. We haven't seen an application of this representation yet, but we will. Then, of course, once we have this more abstract representation type, then we need to have functions do it. Once we write functions, we should write tests. So some of this is about testing eagerly. Some of this is about adding abstraction, but then another part is that we've seen a couple of cases where we started with type synonyms and then ended up going to new types so that we could define custom instances and we could maintain invariants. The other thing that we're seeing is that we see there's these sort of parts of the files that are forming. So like all of this stuff, there's a bunch of operations on vectors. There's a bunch of operations on Wordle words, right? I imagine that at some point we might even be tempted to break these out into other modules to continue to enforce sort of separation of concerns. So these are some of the trends that we're seeing here. Thanks very much for watching. More next time. Bye.